What is his model kind of famous for?
Energy levels.
Okay. What else? I mean,
like planets.
yeah, right. This the one that we use the most to explain, which has nothing on it, but you have seen this, right? With the whole orbiting things. Okay, Bohr's model is probably the most famous in that it's probably the easiest to like explain the constructs of an atom the best, even though it's not 100% accurate. Okay, what about this isn't 100% accurate? You guys know? Yeah, they don't orbit in circular motions. Okay, electrons really, yes, they do some sort of orbiting, but it's not like you think. Okay, they exist in orbitals, and the whole idea of orbitals is actually very, very, very complicated. Because what an orbital is just a probable region of electron location. It's like we think an electron is going to be in this area, this region. And yes, they've got math to support it. And I actually, if I can find some pictures out of my advanced chemistry book, that will show this a little bit better. Okay, but the first thing I do want to address, his biggest contribution was this. What he did is he was able to identify that there are various energy levels within an atom. Now this is something that you will hear if you take advanced chemistry. We talk about it a lot more. It's called the idea that energy is quantized. You may or may not have ever heard that word. And it has to do with these energy levels. Energy can only be distributed in certain whole number amounts, or a certain amount. You can never give half of that amount. For example, when we were dealing with energies, let's say there's energy level 1, that's energy level 2, that's energy level 3, and so forth. Before I explain this any further, let me explain on the periodic table where energy levels are, because it's on here. Does anybody know, did we talk about it all in physical science?
I feel like we did, but I don't remember.
Okay, energy levels are your periods. First energy level, and they're your horizontal rows. Okay, second energy level, third energy level, fourth energy level, fifth energy level, and so forth. So let's just say we're talking about magnesium. Okay, do you remember the 288 idea?
Oh,
Yeah, and then it was like 2, 8, 8, 8, 32. Okay, that has to do with how electrons fill certain energy levels. Well, look at how many electrons fill the first energy level. 2. Does that agree with the 2, 8 idea? How about the second energy level? Are there 8 of them?
Yeah.
How about the third energy level? Well, that one's a little debated, but we'll get to that later. Or not debated, but it's a little more complicated. We'll get to that a little bit later. But I'm just trying to show you here that if I'm talking about magnesium has how many electrons? 12. The first 2 electrons of magnesium are in the first energy level. The next 8 are in the second energy level. And there's only 2 that are actually in the what level? Third. Does that mean it doesn't have a 4th, 5th, 6th, or 7th energy level? They're there, but is there any electrons in there? No. Think of like a hotel room. Got all these rooms, correct? Okay, got all these different levels, different floors. Okay, with all these rooms in them, but are all the rooms always occupied?
Yes.
No. Okay. Now, the lowest energy level is energy level 1, and we would call that the ground state. Okay? Or you could also say, like for magnesium, having all of the first full, the second full, and the third up to here full, as long as they're not excited or any higher than what they should be, that's in the ground state. Okay? That just means it's in its most stable state. It's not higher than what it needs to be. Here's why. Sometimes you can take an electron from the first energy level and you can give it energy. You with me, Brevin?
Yep.
Okay? It's what you would call exciting an electron. Give it enough energy that it will go up to energy level 2. But believe it or not, if you don't give it enough energy to get all the way up to level 2, it won't leave energy level 1. Like there's no such thing as going halfway between, or 1/4 between, or 3/4 between. That's the whole idea of quantized. Believe it or not, energy gets transferred in packets, not like whatever amount you want. That's kind of a weird idea to think of, but it's reality. Okay? So if I give it enough energy, it could jump up to energy level 2. It could jump up to energy level 3, which has more energy. You guys understand that as you go up in energy levels, you have more energy? That should make sense. Okay? This is what happens when you blow up a firework. What you're really doing is when you ignite the firework, it has enough energy to excite electrons to a higher energy level. Well, if it has higher energy, does the electron really want to stay in its unstable high energy state? No. It wants to go back to its ground state or where it's most stable. And so what those electrons do is they drop energy in the form of what? Light.
And noise.
And yeah, electrons don't give off energy in the form of sound. That's the result of, exploding gunpowder and stuff like that. But, okay, the light comes from electrons that have been excited out of their ground state to a higher energy level, and then they go back down because they're not stable, and they emit the energy that they gain in the form of light. Okay? And this is really what led Bohr to get his rings. He thought, as you go further out, it's just a spherical ring, but the further are you away, the further electrons are away, is due to the fact that they have higher energy. Because, think about this, they're attracted by what in the nucleus? Protons. So the more energy they have, the more they could break away from the protons in the nucleus. So, this is the 7th energy level. Okay? The electrons at the 7th energy level have much more energy and are a lot further away from the nucleus than ones in the 2nd energy level, and so forth. Okay, that should make sense. He was right that as you got energy, you got further away, but it doesn't do it spherically. If that makes sense. Okay? The orbit isn't a circle. Okay, let me see if I can show you some pictures of orbitals. We'll see this in a later chapter, but oh, I guess I don't have some pictures. I thought I had some. But there are some examples of what orbitals look like. We'll see them much later. But if you look at, they're not spherical orbitals. Find that picture. I don't know where they are. But you can see a bunch of them there. There's a bunch of orbitals that kind of overlap each other. That's methane, actually. Or no, that's a form of methane, or a form of a hydrocarbon. Okay, there's some more orbitals. Okay, so they're not actually spherical, per se. We'll talk much more about an orbital later. But what Bohr's really main contribution was, is that there were various levels of energy and electrons. Okay? Questions so far? Okay, we already talked about his problem. Great that he discovered the energy levels. However, they didn't orbit like planets orbit the sun. So that led us to the quantum model, which is the model that we have and assume to be true today, which just simply takes Bohr's model, and instead of having it orbit around like planets orbit the sun, what we have is we have orbitals. But here's a couple things that make this very difficult.
Dipperally?
we're not going to get super deep into these. These are some of the deepest concepts in chemistry. The de Broglie's hypothesis. It's this concept that if waves can behave like particles, then particles can behave like waves. This is probably one of the most difficult things, is the wave-particle duality. You guys know what that is?
There would be a wave and a straight line at the same time.
Yeah. So particles, or any object, acts like a wave and a photon, and a photon is straight lines. How can you be waving and going in a straight line all at the same time?
It just feels super fast.
Man, the evolution's awesome.
You know, I'm not going to get crazy deep into this. I do much more in advanced chemistry, but what ends up happening is the bigger the object is, the more it acts like a photon or straight line motion, and the less it acts like a wave. The smaller the object, the more it acts like a wave, and the less it acts like a photon. And guess what falls right in the middle of that spectrum? The one that has kind of 50-50 traits of each. Guess what falls right in the middle of the size spectrum? Electrons. So electrons have part wave properties and part straight line photon properties. It is very, very, very difficult to understand electrons because of that. And that's kind of one of the reasons why we have Heisenberg's uncertainty principle, and that's part of the reason why our orbitals are what? Probable position. Does it say we know that an electron is here in an orbital? No. They have no idea. Let's read Heisenberg's uncertainty principle. The principle that it is impossible, mathematically, they say it's mathematically impossible to know both the energy or momentum and the exact position of an electron at the same time. Can't be done. Makes it hard to come up with a model that we can say is 100% accurate, doesn't it? So we are going to talk surface level stuff about electrons, but just know there's a lot of stuff that scientists have not discovered and do not know. Trying to understand the depth of God's creation is not quite as easy as we probably had thought. Right? So, what does quantum model look like? I think there's a better picture here. I just have to find it. Reset.
Suck acid. The holy suck acid.
It's just a hard step, like my legs, I think.
Just like you got the
It's just like, this may be so for some reason. Yeah, I feel like
the holy suck acid is good.
that's so freaking better than the others. Like, you just really like it.
Alright, this is the picture I was looking for. So these are just some examples of some orbitals. I don't know if you all can see that, but there's your p orbitals, which we'll talk about in this chapter. We'll talk about all the types of orbitals, s, p, d, f, and even theoretical g. Okay?
But wouldn't all of them be
And now notice the picture that they see over here. That's based on mathematical calculations, the likely possibilities electrons could be.
So they really have no idea.
They really don't. It's a probability. Because of Heisenberg's uncertainty principle, they can't know the exact position and know its energy at the same time. Wasn't that pretty important from an energy level standpoint, knowing energy and position at the same time? Can't do that. You know, what they end up doing is have to mathematically do probability, which probability is quite a bit challenging to do. If you think probability in like algebra 1 is like Oh, probability is easy. There's classes, whole classes on the concept of probability. It's very, very, very difficult. So just know, you can see here would be your d orbitals. We'll talk about those. Okay. Now, obviously, there's certain places that it's more dense or more likely for electrons to be, but it's possible that they could scatter further out, and it's due to the fact that they have energy, and not always are they moving at the exact same speeds at all times. And is it possible for electrons to somehow get a little bit further away than maybe it would normally be? Yes. I love that one. That's like the double-sided pacifier. It's my favorite orbital.
Wait,
It's
that's
like
a thing?
two twins.
I've never seen that before.
What?
I don't.
No, it's not. I don't think this is
Oh,
but
I was
doesn't that look like a double-sided pacifier?
Yeah.
Yeah. Like if you ever have twins, get a d orbital. Best kind of pacifier you can get. Not funny. That was stupid, Mr. Kramer. Okay. So how do you draw the quantum model? Good question.
You don't.
You kind of don't, because the quantum model is three-dimensional. So I'll try my best. In the middle of the atom, we got some protons, we got some neutrons, so forth. Then the s orbital actually is pretty spherical. But our p orbitals actually look like dumbbells.
Ooh, it's like a fan. You just drew a fan.
And I need to do, so this would be x, that would be y, and now we gotta do z. How do I do that? Z-axis.
It's
Draw
like,
it, like,
have you seen the
on a
pen
slant,
things?
like-
Like,
You could try to do it on a slant. That would be the best way to do
Yeah,
it.
have Rachel do it, honestly.
But it's not two-dimensional, right? And then you got your d orbitals, and you got your f orbitals, and we'll talk about that. You can see up here, there's an s block, an e block, a p block,
I've
and an
always
f
wanted
block.
those, man.
And we will talk, what we're going to be doing over the next couple days, obviously next week, is we're going to start identifying all the types of orbitals, what energy levels those orbitals are in, how many electrons can be in those orbitals, when they'll be in those orbitals, when they won't be in those orbitals, how to identify them, and so it's going to be a considerable jump up from what we've been doing up to this point. We've been kind of just reviewing. Natalie.
I'm trying to, there was like a 3D pen thing I've seen before. And I was trying
Oh,
to
really?
Yeah.
So, is it pretty easy to draw a Bohr's model?
Yeah.
Yes. Okay. Quantum model's not easy, but you can probably figure it out. I'm gonna look at your worksheet. I'll be right back. We can shut this off. We don't need this anymore.